Hello, beautiful humans. Welcome to AP Stats. We are in section 10.2. I'm actually towards the end of the packet. I'm at the bottom of page 9, and we've got this problem about bounty paper towels. And so let me just give you a brief rundown of what's happening here. We've got two AP Stats students for a final project. They have decided to compare bounty paper towels to generic paper towels. And so what's happening here is they have decided to wet these paper towels with, it says 4 ounces of water. They have 30 generic paper towels and 30 bounty paper towels to do their test. And what they're doing is holding the opposite edges of the paper towel after it's wet, and they're literally putting quarters on the paper towels until it rips. And what they have representing here, all of these numbers in this table, represent number of quarters that the paper towel was able to hold until it broke. And so what we have here, I'm not going to spend too much time on letter A. What I did is I graphed these two box plots in my graphing calculator. And it appears just by looking at these numbers that the bounty paper towels are significantly better, stronger, if you will. They hold more quarters after getting wet than these generic ones do, but maybe this happened just by chance. At what point do we say, yes, bounty is better and generic is not? So what the first part of this problem wants you to do, which I'm going to skip for the time being, is to compare these two box plots. So just remember, as an FYI, this is going all the way back to, I think, the very first thing I taught you in chapter 1 was when you see the word compare, that means you need to use the acronym SOX. Shape, center, spread, outliers. Anyways, again, like I said, I'm going to skip this for the sake of this video. But what we have is it appears, I've written like just a generic statement down here, it appears as though the absorption capability for bounty is significantly higher than generic. So enter chapter 10. We have two samples. These numbers represent means and not proportions. So these aren't percentages. We're counting actual number of quarters and we're going to average them together, which is why I use the word means. And we don't know the average of the population, and we don't know the standard deviation of the population. So what we have here is our very first two sample significance test for the difference of two means, and we're going to be using a t-test because we don't know the standard deviation of the population, as opposed to a z-test. So flip the page. All right, guys, so use a significance test. We're in part B. I basically skipped part A. You're welcome. Use a significance test. So that means we're not doing an interval. A significance test means write a ho and a ha and come up with a p-value and reject or fail to reject. So use a significance test to determine whether there is convincing evidence. Those are some more clues in the wording of the question that you're going to be doing a test and not doing an estimate, which is what they say when they want you to do an interval. That wet bounty paper towels can hold more weight, one-sided, keyword, on average than wet generic paper towels. So as you know, the very first thing we're going to do is we're going to define some stuff. So going back up to all these letters here. So what I did is I popped all these into my calculator. You don't need to worry how to do that right now. I'm popping all this into my calculator, and what do all of these things stand for? I'm going to use X sub B for bounty. These are all my different X values for bounty, and I have a bunch of different X values for generic. So that's the first thing that I'm going to define. And again, let me remind you that if I go too fast, you have the ability to pause, copy down, and then play when you're ready. Okay, so like I said, I've defined X sub B as the capacity of bounty paper towels. Even though it's obvious what the XB versus the XG stands for, these are the things that are going to bump you up instead of bump you down and get you the 5 instead of the 4 on the AP exam. You have to be very thorough and very clear. The capacity is being defined in this problem as quarters. They could have used anything to decide put something heavy on the paper towels, but they just decided to use quarters. So that is how I'm measuring all these X values. I'm also defining the populations here. And then I need to come up with a ho and a ha. So remember, a null hypothesis, when you're doing a significance test and you're comparing two things, in this case we're comparing bounty versus generic, the null hypothesis, the ho, is always assuming that there is no difference. No difference at all, they're the exact same. We're looking for evidence to reject that. And so the way I'm going to write my null is I'm going to use the mean capacity of the Bounty paper towels minus the mean capacity of the generic paper towels. These are averages. That's why I'm using the mu symbol. I'm not taking just one individual x value from Bounty and comparing it to one individual x value from generic. I'm taking the means. So important to note that we're using that symbol of mu. When you subtract them, you get 0. And my alternate hypothesis is Bounty better? Can it hold more quarters? So when I subtract generic from it, is that difference greater than 0? There is our one-sided alternate hypothesis. Keep in mind, I've said this in class before, there are multiple correct ways to write the ho and the ha. Sometimes you will see them as being equal and one being greater than the other. For some reason, I'm just more comfortable putting zeros. I don't know why. This is also perfectly acceptable and correct. It means the same thing mathematically. As we get into more complex ho's and ha's, there will be a lot of different ways to correctly write them, so just be prepared for that. My introduction sentence, since I am testing something, I have two different something. Remember, we have an introduction sentence to explain what it is exactly we're going to be doing, what kind of test we're going to be doing, and why. So just keep in mind that the sigma being unknown is really important because that is why we are doing a t test and not a z test. Friendly reminder, for proportions, which this is not, but when we do a proportions problem, we always use a z. Okay, so when we're doing a means problem, occasionally we've done problems where we are given the sigma for the entire population. That is rare, but when you're given the sigma, it's okay to use a z here. Here we do not know the sigma, it is unknown, and that's why I'm using a t. So that, I think, is probably the most important part of this introduction sentence. Go through your random, your independent, your normal really quick. We do have a random sample. If you want to flip up to the wording of the question, we took 30 of each type of paper towel. Independent, make sure that you've got 2 checks here. Remember, you do 2 checks for independence. You have to make sure that the generic and the Bounty paper towel samples are actually independent of each other. They're 2 totally different brands altogether, so it makes sense that those would not impact each other in terms of our experiment. And I do believe that it is reasonable to assume that there are more than 300 of each type of paper towel in the population. Hence, we have our 10% condition met. Again, I know I'm going really fast. Pause the video and copy down, and then play when you're ready. The normal condition. Okay, so for normality, what we check first of all is NP and N1 minus P, but wait, we don't have P's. Okay, so problem number 2 is we look in the wording of the question. If it's a means problem and we think to ourselves, does it say anywhere that the distribution of number of quarters that each paper towel can hold is normal? It doesn't say that anywhere up here, dang it. Option 3 is, oh, can I apply the CLT? Yes, because in fact, the sample size is just big enough for both of these that I can apply the CLT. Remember what you say after you're applying the CLT is it is safe to use T. That is because I'm using a T distribution here. So it probably wouldn't be the best idea to say the CLT applies, our sampling distribution is approximately normal. That implies that we're going to use table A and do normal CDF and stuff like that. In this case, we're using a T distribution. So the fact that we would say, if you would say that it's normal, doesn't really apply to this problem. We're using T's here. Take a second, if you're okay with these condition checks, same exact checks we've been doing all chapter long, and in fact for the past 2 chapters pretty much. I wrote down a bunch of statistics for you. In normal school years, we expect our students to be able to type this into 2 different lists in the calculator and very, very quickly be able to spit out all of these statistics. So the mean for Bounty, the mean for generic, the standard deviation for Bounty, for the sample, these are S's by the way, just the sample of 30, the standard deviation of the sample of generic. I'm also going to write the sigma, 0.05, none was given, so I'm just assuming it to be 5%. And the degrees of freedom that we're using, you take your sample size minus 1 equals 29. Just a note, if you have 2 different sample sizes, do you remember what you're supposed to do? You use the smaller sample size, minus 1. In this case, they're both 30. So 30 minus 1 means our degrees of freedom is 29. I'm going to be looking at row 29 in table B after I get all my statistics crunched here. Okay, so I would give you this information in this remote learning scenario that we're in, okay? So don't panic. You don't know how to get this in your calculator right now. That's okay. I will give you that info. But what you need to know is, what do I do now to come up with my test statistic? Here's the words that are written on the formula sheet. You need to know what your statistic is for this problem. The statistic is the difference in our two samples. So this number minus this number, the bounty minus the generic. That difference between those two sample statistics is the statistic for our problem. The parameter is the number from the hoe. Remember, we're always assuming that there is no difference, so that's going to be a minus 0. I like to write the minus 0 because I like to fill in all my blanks, but obviously minus 0 does nothing. What about standard deviation of the statistic? So we have two of these. Let me go back to the formula sheet really quick because it's on there under two sample, difference of sample means. Here's the formula. This you have in your reading guide, and it was in the other example we did in class, but when you don't have a sigma, you replace it with the sample standard deviation, the S sub x. In this case, the S bounty and the S generic. So here's the formula for the standard deviation of the statistic. Everything's there, but it's kind of like doing a puzzle. You got to put it together. So anyways, I'm going to plug in all my symbols first. That is how I'm going to fill in statistic minus parameter over standard deviation of statistic. I'm going to now plug in the values. All those values are right here. I took them from my calculator. I will give them to you so that you can just crunch this number. Hardest part of this whole problem is typing this correctly into the calculator. I encourage you to pause the video and try it, okay? That gives us 17.644. So what is the probability that the T, the test statistic, exceeds 17.644? How do I do that in table A, or table B, excuse me, because this is a T? Well, remember, I'm doing degrees of freedom, which is 29, so I'm going to look at row 29, and I am finding the closest number I can in that row to 17.6. Let's see what I come up with. Flip all the way to table B. I'm looking at row 29. Let me erase this. Here's row 29. Wow, it maxes out at 3.659. What do you think that means? Usually we've had test statistics that are like 2 point something. So that means 17 and some change is going to be like way over here. So what is the p-value? Wow, look at all these. It's getting smaller, 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 smaller. The p-value out here is going to be really, really close to 0, my friends. I know that's really annoying that we can't come up with an exact value, but if you think about a t as kind of being a little bit like a standard deviation, can you imagine moving 17 standard deviations above average? That would put you at a p-value of so small that you wouldn't even really be able to shade anything. So it's about 0. And that is how I come up with my p-value. So what do we do with that 0? Is that p too low? What are we comparing it to again? We're comparing it to 0.05. Is this p too low compared to that? Yes, it is too low. The ho ain't your ho no mo. We reject the null in favor of the alternate. Here's how you write your conclusion. Since the p-value is about 0, that's for sure less than alpha. That means we reject the null in favor of the alternate. And remember, that means you restate the alternate in words. That the capacity of bounty is, in fact, higher than the capacity of generic. So this p-value is so unlikely to happen, assuming the null is true, so assuming there's no difference between the two. For us to get sample differences this large, I mean, look at those averages. In terms of number of quarters, that seems to me like a lot of quarters. For that to just happen randomly by chance, if there really is no difference, the chances of that happening are so small, then that leads me to believe that the ho is actually false. Okay, so I'm going to reject the ho. I am now in favor of the alternate. We have evidence to support the fact that bounty is better. So part C just tells you not to conclude. I did my conclusion up here. Do you remember how to interpret the p-value based on the group work I graded from a couple days ago? It seems like we still maybe need a little bit of work to interpret the p-value. What does that p-value mean? So just remember, I'm going to draw a sketch. The sketch helps me illustrate what's happening, assuming that the hoe is true, which means no difference. We have a almost way out here. What's the shaded area way out here? Almost 0. 0% chance, assuming the hoe is true, of getting a sample difference like ours or shading even farther to the right. That's harder to shade because there really isn't a shaded region. The shaded area is basically 0. But remember that your interpretation of the p-value, which is the shaded area, which is about 0 way out here, you start by saying if the null is true in context, there is a 0, in this case, % chance of observing a sample difference greater than, because I shade to the right because my alternate was a shade to the right situation, to the one we observed, the statistic, so the actual difference between the two paper towels. Here's what it looks like according to this problem. If I'm stating the null in context, the mean capacity, blah, 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 for bounty and paper towels is the same. There is about a p-value 0. So this is like the fill in the blank sentence. Here I actually am filling in the blank. This you can get from the textbook. Here it is in terms of the paper towels. So I'm filling in the blanks here. Chance of observing a sample mean difference greater than or equal to, this is the direction of the alternate. We shaded to the right. We wrote a ha with a greater than sign. So greater than or equal to the one we observed, which in this case, the difference between the two, the statistic that I used way up here, this number was almost 30 quarters, which is huge. So just remember, I have a note for you here. The p-value is a probability of getting a sample like ours or more extreme just by chance if we are assuming that the hoe is true. So if we have a really, really small p-value, that is very unlikely. Therefore, we have evidence against the hoe. We actually think that our bell curve is probably centered at the wrong place. Okay? So there, my friends, in a nutshell, is how to do a 2-sample t-test for means for chapter 10. So thank you for watching. Have a great night. Please bring your questions to class. I'll see you guys later.